So our fourth and final talk will be from Abby Citterman from the University of Utah, and Abby is an undergraduate student, and she'll be discussing artificial sensory feedback.
Hello, my name is Abby Citterman. I'm an undergraduate researcher with the Utah Neurorobotics Lab, and I'm incredibly excited to share some of my research with you today. We'll be discussing electrocutaneous stimulation, which is a low-cost, non-invasive method of restoring sensory feedback, and the fact that low frequencies improve intensity discrimination. Understanding this topic is key to providing prosthetic solutions that will help restore sensory feedback and truly restore the sensory experience of an intact human hand. So restoring sensory feedback after upper limb loss is essential. Up to 50% of upper limb amputees abandon their prostheses within 1 year of use, citing the lack of sensory feedback as a key factor to this. The implications of this are twofold. Firstly, with respect to functionality, the absence of sensory feedback inhibits fine motor skills. Further, it has great emotional implications as well. Consider the sensation of feeling the touch of a loved one. Also, the sense of disembodiment is another critical factor for prosthesis abandonment. So restoring sensory feedback can help foster that sense of unity with one's prosthetic device and help encourage that recreation of the human sensory experience. So in an intact individual, the perception of tactile stimuli is that mechanoreceptors in the hand receive and are activated by external stimuli, and these are then rapidly transformed into electrical signals, which propagate as action potentials along the nerves, where they are consciously perceived as touch in the brain. Conversely, in an individual experiencing upper limb loss, the mechanoreceptors in the hand are no longer present. So the afferent nerves that transport that signal are still functional. So artificial sensory feedback seeks to bypass traditional mechanical transduction and provide its own electrical encoding by receiving the stimuli and the information instead from sensors embedded in the bionic hand, applying its own artificial encoding, and directly stimulating the nerves, upon which action potentials will propagate along those same natural pathways and be consciously perceived as touch in the brain, as though it were coming from the missing limb. So methods of such stimulation vary greatly in cost and invasiveness. Intraneural stimulation, such as that with the Utah slanted electrode array, and epineural stimulation with the flat interface nerve electrode are two examples of more invasive methods of stimulation. These are implanted in or around the nerves, and while they have been shown to provide sensory feedback in this capacity, they are expensive and they bring with them the heightened risk of infection. Electrocutaneous stimulation, alternatively, illustrated here with our custom fabricated stimulation pad, is a low-cost and non-invasive method that evokes tactile stimulation through electrodes on the skin. So using this, we have improved accessibility to artificial sensory feedback, but we do want to ensure that there's still high-resolution feedback restored with this. So to that end, we sought to identify the maximal number of sensory gradations that could be achieved with these artificial methods of stimulation. Here we see the psychophysical function of an intact hand and their perception of intensity across the span of external stimuli. And we see that this is a smooth, continuous function over which perception is felt. And we are curious how that looks with a bionic hand with the implementation of artificial sensory feedback. So we hope to examine the implications between the different methods of stimulation to see if non-invasive electrocutaneous stimulation can be an effective surrogate for these more invasive and inaccessible methods. So to that end, we set up a two alternative forced choice paradigm, and we modulated stimulation frequency, and we asked participants to judge which of two stimuli felt stronger. So if the test stimulus were of a much lower frequency than the reference stimulus, the probability of it being judged stronger would be 0. If the test stimulus were of a much higher frequency, the probability of it being judged stronger would be 1. And if the reference and test stimuli were equal, say 50 hertz compared to 50 hertz, the probability of either being judged stronger would be 0.5. This is then visualized by the J&D trace, the psychometric function we see here, asymptoting at 0 on the left with these lower frequencies, and asymptoting at 1 with on the right side with the higher frequencies. And this shows the just noticeable difference, which is the minimum change in stimulation frequency that can be identified correctly 75% of the time. This is guided by Weber's law, which states that the J&D is proportional to the absolute magnitude of the stimulus, or in other words, the greater the intensity of the stimulus, the greater the change needed in order to be able to perceive that change. And this then leads us to the Weber fraction, which is the normalized J&D, and that allows us to compare discriminability of these different methods of stimulation across reference frequencies and across the different methods of stimulation. So the major takeaways of my talk will be that, first of all, intensity discrimination is improved at lower frequencies, and second, that electrocutaneous stimulation can serve as an effective surrogate for those more invasive methods that we talked about earlier. So to start, we'll dive into that first point, that intensity discrimination is improved. So here we see a psychometric function like we saw earlier. This is the just noticeable difference. And the sharper a psychometric curve, the improved the performance. So this one here is at our 25 Hertz standard, which is our lowest frequency standard. And we can see that that range between the 75% to be able to be judged correctly is a very narrow window. This is at our 50 Hertz standard, and we can see that the curve is slightly gentler, and that window is a little larger. Then at our 75 Hertz standard, we see a much larger window, much gentler curve, and that indicates a further disprovement of the discriminability. And then 100 Hertz standard is our highest frequency standard. We can see that this is our gentlest curve, or that largest window needed to be able to detect that change. Those same 4 frequency standards are now shown with their Weber fractions, which is the metric that normalizes it and is able to compare across. And if Weber's law were to hold true, we would expect all 4 of these to have the same Weber fraction affiliated with it, because it's the percent change that should be detectable. But we see that for at least electrocutaneous stimulation, Weber's law does not hold true, because we have significantly improved performances at these lower frequencies. This can help guide our future implementation of what stimulation parameters will provide the most intuitive and natural sensory feedback. So that brings us to our second major takeaway, that electrocutaneous stimulation can serve as an effective surrogate for these more invasive methods. Here on the left, we see the same 4 frequency standards and their Weber fractions that we saw on the previous slide, and we're now able to compare it to the intraneural and epineural Weber fractions from previously reported literature values. We can see that electrocutaneous stimulation yields comparable discriminability, if not enhanced. So if we were to compare in navy blue electrocutaneous stimulation at our 25 Hertz standard, we have a Weber fraction of 0.1. Comparing that to epineural at the 15 Hertz standard, that Weber fraction is significantly higher, demonstrating that at our low frequencies, we have increased performance and better discriminability, which shows that we have it's an effective surrogate to provide intuitive sensory feedback. This then can also be used to estimate the number of sensory gradations that can be perceived with these different methods of stimulation. So to review, this is the psychophysical function of the intact hand, smooth and continuous over the span of intensities. If a method of stimulation were to offer 2 gradations, that would just be discrete on-off. If it were to offer 3 gradations, we would soft, medium, hard. And so epineural stimulation offers 18 sensory gradations. Certainly much better than the binary on-off would be, but far from that smooth psychophysical function of the intact hand that we were looking at earlier. Intraneural stimulation has 26 sensory gradations, so an improvement from epineural, but we're still a bit away from that nice smooth curve that we saw earlier. And then electrocutaneous stimulation. While we still do have those discrete steps of perceived discrimination, we see that this is finally starting to look like that natural psychophysical function of the intact hand. And this demonstrates that electrocutaneous stimulation can be an effective surrogate, not only with respect to its low cost and its non-invasive nature, but that it offers high resolution sensory feedback as opposed to the more invasive methods. We believe that the improved discrimination may in part be aided by timing cues. So at these lowest frequencies, we can still feel the spaces in between the individual pulses, and it's more of a tapping sensation. whereas at those highest frequencies, it's a constant pulse and more of a vibration. So we hope to adjust our experimental paradigm a bit to isolate frequency percept to make sure we're implementing the most intuitive artificial sensory feedback possible. So in summary, the major takeaways of our discussion here was that intensity discrimination is improved at lower frequencies for electrocutaneous stimulation, and that electrocutaneous stimulation is a low-cost and non-invasive alternative to those more invasive methods of stimulation, while still offering high-resolution feedback, comparable if not improved as to those more invasive methods that have been proven to work in the past. So with that, I would like to thank our sources of funding, our collaborators, and everyone at the University of Utah that has helped make this work possible. And most of all, I would like to thank all of the volunteers that have come in and dedicated their times and their bodies to our work. And at this time, I welcome any questions. Feel free to email me or the principal investigator, Dr. Jake George, if you have any questions that aren't able to be answered today. Thank you so much for your time. Yes, so the question was, we've explored a lot with intensity discrimination, so what about location perception? So with the way after amputation that the nerves grow and the residual nerve still in the residual limb, there is mapping that can be done to detect. So for an amputee participant, we can find what nerves can be stimulated in order to feel sensation, not only from the missing limb, but specifically from a missing finger or the palm area. So we're in initial stages of that right now, and some really exciting applications in the future with that. Great question, thank you. For the electrocutaneous stimulation, perfect. So the question is what kind of electrodes we're using. So we custom fabricate these ourselves. They're stainless steel brads that we have soldered to the wires, and then they're embedded in a silicon pad that we 3D printed a mold for. No gel. We use medical tape to tape it onto the skin to ensure optimal contact. So there were the 5 electrodes. The one in the center is the stimulating electrode, and then the foreground around the outside. Perfect. So I'll start with the first question of are we stimulating in different locations? So our previous studies have shown in our lab that we can stimulate on the palm or on a residual limb and yield very comparable results. So all of our studies have either been on an intact palm or on a residual limb in a standard location, and we're not modulating that, but we do believe that we could implement more stimulation and do the mapping that we discussed earlier in order to have more specific percept. And then could you repeat the second question for me? Pressure. So it's an interesting concept with electrocutaneous stimulation specifically, that intensity is felt over the span of frequencies, and you can also modulate amplitude with that as well. So we have explored both of those to try to see what will best isolate frequency.